The online version of MATLAB, time to time, the thing just randomly disappears, it seems. It's stopped. ODEs. I didn't even touch the thing. So initial values in this array, I parcel up the two equations just for niceness into this array called equations. Then I call dsolve on the equations and the initial values. Now this is the output it's giving me here, the so-called strut. So MATLAB strut, it tells us a structure with two fields, a y field and an x field. Now something curious goes on here. If you want to examine those, examine the actual solutions, we got to assign the struct to some variable sol. Then I can call sol.y and sol.x. So that should output just execute that block again. That should output the solutions. And when I was first doing this, I was hoping to see the nice solutions we found this morning. And I was a little bit perturbed at the start. These two expressions here, which initially don't look right. Well, what's going on here is MATLAB has solved the equation symbolically, but it hasn't done a kind of final symbolic simplification. So while these functions are correct, they're not expressed in the nicest form. You can see there's going to be some cancellation here. Look, you've got exponential to the 5t multiplied by this factor here, but it has a factor exponential to the minus 5t. So that's going to cancel off with each other, simplify somewhat. Similarly here, we have an e to the 5t times e to the minus 5t. So once I spotted that, I realized, oh, it just hasn't done, it's simplified the expressions very much. Symbolic simplified command is simplify, and that should look to see if there's any simple, straightforward algebraic simplifications it can do on those quantities. So when you call simplify sol y and simplify sol x, yeah, we get the two solutions. You'll remember them from this morning. The solution to y was 1 plus 2t plus e to the 5t. The solution for x we found was minus 1 minus 2e to the 5t. So you can use the dsolve command for systems of differential equations as well. The other thing we looked at this morning was some partial fractions. I can define, remember this morning we looked at an example where we ended up with this rational function, so a quadratic polynomial over s squared times s minus 5, and we obtained the partial fraction expansion of that. Well, there's a nice command simply called part frac, and I call the rational function rat. So part frac rat there will output nicely the partial fraction expansion of the function. Similarly, there are commands Laplace and Laplace for Laplace transform and inverse Laplace transform. If you call Laplace on some symbolic function, it will attempt to give you its Laplace transform. And similarly, if you call inverse Laplace on a function, it'll attempt to get the inverse Laplace transform. So an inverse Laplace transform on rat there, for instance, it's Laplace rat. It's disappeared again. Monster. Like that web programming by MATLAB here. Or it could be the browser's fault. So basically, I'm just going to do Laplace on rat, and it should give me the inverse Laplace transform. So execute that block, Control Enter. Yeah, 2t plus e to the 5t plus 1. I think that happens to be the same y that we encountered in the other. Oh, sorry. That was the partial fraction expansion we had to do this morning in the example. That was the function y of s, so you can get its inverse Laplace transform. You can read it off. So Laplace for inverse Laplace transforms, Laplace for forward Laplace transform. Just some other relevant commands. Remember, any of these command names, you Google MATLAB and the command, pretty much the top link most of the time is the MathWorks MATLAB documentation. They always explain the commands very well. They've always got little snippets of example code. Copy and paste and adapt to get going. Okay. Any questions just about those commands? These are something you should use in your work. You can use them to confirm solutions you're getting and so on. So I thought to give us some more practice on this, I mean, rather than forging ahead with new material and that, doing well in the course, we're covering things at a good pace. So I just thought this is such a key skill. And if you look at past exams, it's one of the key skills we examine. So the ability to apply the Laplace transform method to solving these differential equations. There's two typical examples that have appeared in past exams here. So I just thought this would be a good chance for you to just make sure you're okay with operating all the mechanics of this, what's going on, and obtaining your final solutions. You can see how the exam setter, which was me in most cases, got a little bit easy on you here and giving you 0 initial value conditions. So that gets rid of some of the terms, possible extra terms there might be in the solutions if those constants had stayed around. Okay. So since it's late in the day, it's best to stay active as much as possible. So do a few startups to get going. And I'm happy to answer any queries that you may have and help you address some of this stuff. Or any questions about anything that I can help you with? How does your map work?
Oh, it's just saying how word X has in
All the possible
Oh my gosh.
Not proof, so this is what to prove that everybody gets the same. Okay, very satisfactory. And see, how are you going to go about getting your smallest possible set? So are you claiming that this Z is the smallest?
No.
Sorry?
There's a smaller.
There is a smaller. Okay. Well, I can identify it. So like, I'm not allowed to testing every.
Well, get
So like, it looks like good work in it. The two things I want more an explanation of why it is everybody.
Yeah, it's just like,
I mean, that's what will prove that. But maybe there's a deeper explanation. And then, but it sounds like, the things you talked about, the things you mentioned, and you've already maybe argued that you realize that there is a possible smaller number. So you should justify these things and explain them with reference, talking about visibility, CD, well, my live scripts are good for confirmation and verification stuff. That's very good.
Okay.
Everything's there. Right? On up several things. Explanation. It's just
Is it a quadratic?
Yeah.
It's a quadratic. There's like other F's. What are the F's? Well, that's 3F squared. I'm on about this side. Wow.
Are you trying to factorize?
Oh yeah.
People trying to factorize.
It does. So what is 3F? That's what's going to be Shush. I don't think I've done it the right way. No, you need to get a plus. Wait. Yeah, I've done it. That needs to be a plus 1. It doesn't work. Alright. Well, we're comparing it again. That means we're going to have to put it in that weird called something sign ones. So it's it's an odd number. Yes, you can.
Yeah, so the question there, no.
Oh, no, it's just the register.
Oh, the register.
I don't need your help. I just need to sign in. She keeps finding it very amazing. So basically, I basically got told by John she acted like I was reaching a dangerous level of sass last week. She was literally just went to what is he bad at? I think I go too far. You didn't quite push it too far. You didn't do it too far, but it was actually like he put it on me, and I said it's stress. And he explained to me, and then I did, tone it down because he was starting the lecture.
So it's the fact is it's going to see. Would be worse.
So am I gonna go? I want wait.
Yeah, you don't know what
Get
that
me
is.
over there.
You don't know what.
You're over
You don't
here.
know what the transfer is.
Yes.
Oh shit, no.
Mate.
Thank you.
Okay.
Wait, what happens to my S though? I can't remember how to do algebra.
That's a problem.
I'm not okay. Do I want one of these? I don't want one of these.
What's my favorite?
I want that one. That's what I want. I was looking at these.
Well, I just meant like one of these ones.
No, I want. Do I want half of that, don't I?
I want to do three. You know, like, why did you just divide 3 by 3? Technically, no. Like, I know.
I'll do that in a little bit. I'm ready.
Just conservative.
The feeling is mutual.
My question is, would you partial fractions with the S and the 3S?
Well, yeah, because they supply to us. So in this
Oh, it
problem,
makes a lot of sense.
so it's a practice decision.
Just dead.
And then change it back.
Yeah, yeah. You know, if you look forward to the solution, things were non-zero, they would generate extra terms in the final solution. Is a non-zero initial position. Or indeed a non-zero initial velocity.
Yeah.
Further complicate the evolution, you can get extra terms to do with it. So that's a kind of a simplifying setup of that. Or whatever is at the origin, but it's not actually.
How do you not just think about cancer?
It might take more. Yeah. It doesn't take any more machine. It's just the same idea. The cost transform the whole thing. Solve the it's no more conceptual. Some type of paper. You gotta do the process twice. Well, I mean, in principle, I could ask you either. There's a limit, but you know, you gotta be realistic to be able to complete it in the time. Like pushing people. But you know, you should be prepared for it. I think.
Who's she? Come on. We're all just sat here, just not doing it.
Let's try it.
There will exist a partial.
No, I've given up. I'm doing the 2016. I can't deal with it.
Do you think that's going to be any good?
My theory is, I hope so. Because otherwise I'm just going to cry. I have not got that far. Yeah, no, to be fair, we just can't back it. That's our problem that we're having down here.
Don't tell me it's wrong. Is it wrong?
Yeah, I'm literally. Oh, yeah.
You're reducing it from that X. So you hope to find a partial option
But I know it's not
plus something over that. The numerator there might be something like that. And then you have to reorganize that.
Alex is in the same one. So, okay.
He's gonna get us to do something
Let's just multiply it out. I'm going to try and multiply it out.
I tried that, it was not that much nicer.
So, what kind of expansion you have is some concept of
Why? What?
I just want to see cost.
over the
Cost.
well, the numerator here, because it's
Oh gosh, you really are out. Okay. I just tried
Technically, they don't quite line up.
I need to put the num and
Yeah. F squared.
I can't factorize.
Plus what? So, you know, if t was just t, that would be 1.
So what are you trying to figure out?
Well, I'm trying to make this.
No.
No, it doesn't matter. So then when I started doing that, then I was trying to make it into.
Ah, you're trying to complete the square.
That's the one.
Yeah. Okay.
Factorization.
Yeah. So
I can't.
I did have some. I made it nicer. I got the x out of it. Well, that's what I did, and then I was like, then what? I tried doing it as partial fractions, but that's I was turning it into partial fractions, but that didn't help them very much because I can't do maths.
I just need to make this.
I agree.
all I hear from you is I can't. But
That's
I think
correct.
you've done it correctly.
Yeah,
Right,
but
okay.
that doesn't help.
So then,
So what's your problem with this?
She doesn't
So
know
is
how
this,
to
is
get
this
it
final,
with
is this final thing? So are you doubting what you've done this for? I thought that was what you
well,
were worried
only
about.
because I want. Where does this?
You want it in
There
one of
we
these.
go.
Ah, okay, so you're fine with completing the square.
I think so.
So you took out the three,
Yeah.
and then you go plus 1/3 square that equals square.
Yes.
So we need
3
1/3, we need
s
an extra.
squared plus
Yeah.
plus 1.
So you want to reconcile this. So, okay, this is 3 out in front. So
Yeah.
3 out in front is like a factor, because it'll be in the denominator. So it's a factor there.
Yeah.
So by linearity, that can move in or out.
Yeah.
So that isn't the ultimate problem. That factor of the third. If you
Yeah.
want to take the inverse transform, you can just simply slide it.
Yeah, well, also at the moment I've got 3 on the
Or you just
so I can get
nicely cancel it that way. So then you gotta reconcile that your thing in the square bracket.
Yeah.
So which one is it? Which one is it?
This one is what
Yeah.
I'm doing.
So what's the other? What's your?
That means that.
Yeah, no, I think I just didn't want
Yeah.
it. That's the crux of the matter. I wanted it to be a nice one.
Oh, that bit. No, it's not.
Square we get to.
No, I'm not doing it.
I've tried that, that's not worth it. I don't recommend.
So there you prepare the denominator.
Right, okay.
Now I just need to split it up.
I've been avoiding putting partial fractions for a long time. So I've just started this question. That didn't really help.
Right, but I need this to have root 2
Okay, so
That
is
is
that exactly the right thing? You need to
I'm not
something 2 and 3.
And then plus one
And
I think you knocked on my door at like 20.
Oh, it's not so easy to do those in your head. Yeah, move forward here, you got to introduce the calculus. You were here to be something times s. This isn't necessarily just playing all the times.
Oh, yeah, it'll be S plus A.
And then,
So then it would need to be that.
So you kind of have to go through,
Alicia, it stops
go through
crying
the
out
partial
loud.
fraction process,
Oh my god.
except,
Ignore that bit.
That's what it's, yeah.
yeah, but this B could turn out to be something.
Well, I
times
tried
S
to
plus.
factorize.
Yes. Will you stop? You're as bad as kids. Alicia's done the exact same thing as you, but she hasn't yet separated out. And she just scribbled it all out.
Well, that's because she's an idiot though. At least I don't scribble it out until I know it's definitely wrong.
Oh, my teacher trained me out doing that.
Your x bar was 3 over s.
Telling me.
3 squared plus 2s plus 1.
I just used to get comments back to simply trying to say it's correct. It just stopped it.
I think I've done enough.
Did you not?
Sorry?
Yeah, well, you couldn't still. How did you do it correct then? Well, you could sometimes. It was quite simple. Like, I would.
What was it 2s squared plus 3s plus 1?
You would get the mark.
2s squared plus.
No, 3s squared plus 2s plus 1.
Got it.
But we don't have that S. Let's give it that as well.
You don't have the s.
No.
And some other people down the back have the s as well. So it's
The S is for the transform of 3.
Yeah.
the s is from the transform of 3. When you transform 3 at the beginning, that will transform to 3 over s.
Give it over S. Oh.
Yeah, so that gives you the s.
D times S.
Alright.
So the partial fraction expansion you're looking for there would be something of this form here.
Well, one partial fraction. Yeah, there was one over S and one over
That's
that.
exactly what you said. You said no.
Well, because Kim's done it in a different order, you can do it in partial fractions now, or you could get this as 2 brackets and then do it. I'll fight. Fight.
You can ask Matt, if you got MATLAB open, you can.
Accidentally said
You
know, I'll
How
say
do you
no.
decide that C as C?
That's the rule when you're taking partial fractions with an irreducible quadratic factor. You can't factorize that anymore of the real numbers. Remember the rule was then the numerators are not just plain constants, but you need an order 1 expression in s, something times s plus something
And order 1 expression.
in s, meaning something times s plus a constant.
Order 1 expression.
Right, so which of these?
I can't. I
Right.
still don't know how.
I'll go in front of the.
Well, I mean, the partial fraction process, you gotta go back and look up.
Yeah, I know
Revise
that.
it.
But that's
What's your coefficient?
Well, remember, because
Alright,
when
so basically,
one of the denominators was
whatever you-
quadratic,
square means it
that you
equals
couldn't
it. Whatever
factorize
you-
anymore,
means it equals it.
the rule was the associated numerator that will appear in the expansion will not just be a constant, but constant times s plus another.
That's the problem I had when I
That's the rule
did
for
this.
the defining partial fraction expansion.
Oh, he's doing it.
Order of.
Oh, I see. I see what you mean now. That makes sense now.
Okay.
And that's called an order
Yes,
1
I see.
expression.
Yeah.
That was the problem. We tried to factorize it. We know that.
So then I put, right, yeah, that makes sense. That's why I had B equals 0, which I just can't.
That was my problem in the first place. So what do I need to know?
And S. So now, see that is it. Then I've got
B and S plus C. B.
Oh no, I've got A plus B.
So what it's like?
Oh, I did mine. I've done mine.
Why would you go? Well, I'm your happy with all my choices. Everyone will be like, I mean, that's what I think.
C.
There you go. You're in the same place again.
All right. Did anybody else get those partial fraction coefficients? Yeah? Somebody say yeah?
Three. We've got the three.
Are they correct? Three.
Now we're
I
correct.
don't know.
So phase 3, 2a plus c is 0. There is no s's. So 6 plus c is 0, so c is minus 6.
Oh, of course.
And 3 is 9. 9 plus b is 0. So b is minus 9. Yeah.
Ah.
No.
So did people get it done for your kind of intermediate step. So your solved transformed equation for the first one. So that's your x bar.
I've not written value.
Did you take the 3 out?
I took 3 out.
Then
So I've
you
got,
should have run 2.
yeah, I've got that. I just forgot I'd done that.
Final step will be taking inverse transforms of both sides. Now, taking inverse transform of 3 over s will be straightforward enough, because 1 over s is the transform of the constant function. So the inverse transform of 3 over s will be 3. The inverse transform of this fella isn't so straightforward. Okay, it's some kind of rational function in s. The denominator is as simple as it's going to get. So we're looking for the denominators which have s's in them, and that is these bottom 4 on the table here. You can have sight of the table there, someone. So it's going to be one of these bottom 4. So we need to find this kind of completing the square type expression on that. You notice that the factor of 3 can go. And indeed, we need it to go because we wanted to normalize it so that the s squared coefficient is 1. It's going to be 2s plus 3 over s squared plus 2/3 s plus 1/3. And we can go completing the square on that.
Killing
Yeah?
it.
Have I made a mistake?
Yeah. It should be minus 9s.
Oh, flip, the other way around.
Like,
Vice versa. So the 9 on the s and the 6 over here.
yeah.
3s plus 2. Okay, never mind. So that's going to be s plus 1/3 all squared, which gives you the s squareds and the 2/3 s. It also gives you a 9th, but we need a 1/3, so we're missing 2 9ths. And the 2 9ths will represent as root 2 over 3 squared. So this is our s plus a all squared plus our omega squared. So even here, you're not out of the woods yet. You've got the denominator looking right. But you see, when you have that denominator, the options, the choices you've got for the numerators are either the presence of that constant omega, which for us is root 2 over 3, or the quantity s plus a, which you got to pick up from this bracket here, or the quantity s plus 1/3. Now that is neither of those. But you just got to cajole it into some kind of linear combination of these two. Yeah? But your a is specified as 1/3 and your omega is specified as root 2 over 3. So you just got to kick it into the right form. In order so you can make use of those 2 inverse transforms from the table. Does that make sense? Yeah? So our 3 over s is still there at the front. So what have we got? Well, to get the s, the only way we can arrange the s is by having some amount of this quantity s plus a in the top. Okay? But I'm going to want 3, a multiple 3 of it, to generate the 3s. Well, minus 3 times over this numerator, over that denominator, s plus 1/3 squared plus root 2 over 3. And I want to have s plus 1/3 here, yeah? That'll give me my minus 3s. But then it also gives me minus 3 times 1/3. It also gives me minus 1. But I wanted a 2. So far it's generating a minus 1 constant, but I wanted a 2. So I need an extra 3, okay? It needs to be plus 3. So my missing term is 3 over this denominator. But remember, when I've got a constant over that denominator, on the table, it appears with just the omega. So I'm going to have that omega root 2 over 3 over s plus 1/3 squared plus root 2 over 3 all squared. And the missing thing I've got to do is some correcting coefficient here so that in total, I've got my missing constant of 3. Because I'm trying to regenerate the 3s plus 2. Generating is minus 3 times s plus 1/3. Because I want the s plus 1/3 to match that, because that's what's on the table. So I get minus 3s, fine, minus 3s. Oh, sugar, it's minus 2, isn't it? Flip. Sorry, it's minus 2. It's minus 2, so I get a minus 1. So actually, I just need a minus 1. But again, I can only generate it by an omega over this. So to get minus 1, this coefficient here is going to be minus 3 over root 2. Minus 3 over root 2. So like normally we don't do that. Normally we don't take nice compact expressions and needlessly elongate them and complicate them. But the reason we're doing it is to get this expression as a linear combination of functions that are on the table. And the functions that are on the table over denominators like this come in two forms, the s plus a over the denominator and the omega over the denominator. When you multiply it all out, you get a minus 1 numerator from here, the minus 1 numerator from here, so that gives me my minus 2. And then I get a minus 3 times s, which gives me my minus 3 times s. So the equation is fine. The equation is correct. And I've achieved writing this as a linear combination of functions on the table. So it's prepared for taking the inverse transform. Unless I've made errors. Anybody spotted errors? No? So inverse transforms now. My x of t, and I'm using linearity, the inverse transform of 3 over s. 3. The inverse transform of that s plus a is an exponential times a cosine of omega t. So it's the exponential, the a is 1/3, it's e to the minus 1/3 t, and it's cosine of omega t, cosine of root 2 over 3t. And then it's minus 3 over root 2 times something. That's the linearity, this multiple of this function. So its inverse transform is going to be that multiple of the inverse transform of it. So that's the omega over s plus a squared over omega. So that's the exponential times the sine. So exponential e to the minus 1/3 t, the sine of root 2 over 3t. All right? Seems right. And when you're working with these, it's always good to try and get the confirmation from MATLAB. So we could try doing that. That was number 1. When we wake up MATLAB, we can just check we got the right answer. MATLAB's deeply satisfying sometimes. Here we go. So let's reuse one of these examples. Change it to x. What the hell? It's a derivative of x 2 times. You can adopt the command like that. 3 times that. It's 2 times the first derivative. Plus x equals 3. Myself in equation 3 for the, what do I do here? Do diff x t evaluated at 0, 0, I think. I do that. Equation 1, equation 3. Errors, indexing must appear last, and then index expression. Oh, I believe it's this problem here. X diff t. Okay, so you can see MATLAB solving it for us. Here's the original ODE. 0 conditions, which are off the side of the page. That's the solution. It doesn't look exactly the same as the solution we got, but you can see the presence of the exponentials, the cosine, the exponential, and the sine. And it's got the constant 3. So it's just this 3 root 2, but 3 root 2 over 2 is, of course, 3 over root 2. Yeah? So it is the same. It is the same as our solution. MATLAB's preferred way of representing 1 over root 2 is to write it as root 2 over 2. Okay, let's finish there for this evening.